Hello everyone, so welcome to this lecture series on chapter 19, our last chapter on maintaining air quality. There will be a total of 3 lecture videos that you will need to watch, and this is the first of the 3 lecture videos. Now in this chapter we will be learning about the components of air. After that we will be looking at the pollutants which pollute our air and their impacts. And finally we will end off the chapter by looking at the carbon cycle, how carbon dioxide is actually regulated by processes in our atmosphere as well as in our society around us. Okay, so let's dive into the very first subtopic, which is the components, or what we call the composition of gases in air. So in this particular section, you will need to know what are the main components of clean, dry air and what are their percentages. So just take note, we are looking at clean and dry air here. Now, clean means it's free of pollutants, and dry means there's no water vapor. Okay, so looking at clean dry air, the composition of the gases are as follows. As you can see, the gas that is most abundant is actually nitrogen. N2 is the formula of nitrogen. We need to remember that the elements ending with gen are diatomic, meaning they will exist as two atoms bonded together. So nitrogen N2 occupies 78% by volume of clean dry air. Now, nitrogen is the most abundant gas, yet we do not use it naturally for our body. Nitrogen, however, is very important for manufacturing ammonia gas. And ammonia gas is then used to make fertilizers, which is very important for growing crops that we need for food. The next most abundant gas is oxygen. Again, oxygen exists as a diatomic molecule, O2. Now, oxygen is highly important because oxygen is actually essential for aerobic respiration, which helps to release energy from the digested food for our cells to work. In addition, oxygen is also needed for combustion, burning, to release energy from fuels. Now, let's do a short recap of what oxygen molecule looks like. What's O2? So if you recall, oxygen is 2, 6. So the electronic configuration of an oxygen atom is 2, 6. So it has 6 valence electrons. If it has 6 valence electrons, it actually needs 2 more valence electrons to achieve a fully filled outermost shell. If it needs 2 more electrons, it will share 2 electrons. So what does sharing 2 electrons in the O2 molecule look like? It looks like this. Dots cross, dots cross. Okay, so this is what sharing 2 electrons looks like. Each oxygen shares 2 electrons with each other. So 2 dots and 2 cross. Okay, so that's not the end yet. We need to consider I have 6 valence electrons, I have shared 2. Therefore, there should be 4 more valence electrons left which are not shared. And these 4 valence electrons must also be drawn into the dot and cross diagram. Now take note, these dot and cross diagram shows outer shell electrons only. So you will need to read the question to see whether the question requires all electrons to be shown or just the outer shell to be shown. Okay, so shown here is just the outer shell. So we have nitrogen, oxygen. The next gas is argon. Now argon, it's a very important gas, especially since it's a noble gas. As you can see, argon does not exist as molecules. Argon exists as single atoms on its own. And this is because argon, if you look at the electronic configuration, argon has 18 electrons. 18 electrons are arranged 2, 8, 8. So you can see that argon already has a fully filled outermost shell. And therefore, argon is a noble gas that's unreactive. So we say that argon is the most abundant noble gas in the atmosphere. Okay, amongst the noble gases in group 18, argon is the most abundant, occupying 0.93% of air. Now, argon being a noble gas with a fully filled outermost shell is very unreactive. Another word for unreactive is inert. So this word over here, inert, means unreactive. So argon is used to provide an inert atmosphere for reaction chambers so that the reactants do not react with oxygen or water. There are certain reactants which react really explosively with oxygen or water, and to prevent this explosion from happening, we typically use argon in the atmosphere to ensure that these things don't explode. Okay, so argon is the most abundant noble gas in our atmosphere. And lastly, we have carbon dioxide. So carbon dioxide, CO2, occupies about 0.03 to 0.04% of our air. The percentage of CO2 has steadily increased over the years due to industrial activity, due to cars which burn petrol as fuel. So burning of fossil fuels releases a lot of CO2, and that's the reason why the percentage of CO2 has steadily increased over the past few years. So, while learning the composition of gases, it is important to learn the percentages of each gas by volume in clean and dry air. In addition, it is also good to learn the main uses of each of these gases. Okay? Now, given that air contains these gases, we can say that air is a mixture, and therefore, to separate air into each of these gases, we will need to use fractional distillation. So, fractional distillation is used to separate air into the component gases of nitrogen, oxygen, argon. Okay? So, similar to crude oil, fractional distillation is also used to separate air. However, for air, there's an added challenge. Crude oil is already a liquid, so you can just put the crude oil into the fractionating tower. Air must first be liquefied before it can undergo fractional distillation. Now, why is fractional distillation still a suitable method to separate air? And this is because the gases in air are miscible, they can mix together, and they have different boiling points. So now let's move to the next page where you will see the different boiling points. We don't have to memorize the boiling points, neither do you have to memorize the order. Okay, if need be, the question will provide you with the boiling points of the gases. So over here, I've told you that nitrogen gas has a boiling point of minus 196 degrees Celsius. Because it has a lowest boiling point amongst the gases, it will be distilled out first and is collected at the top of the fractionating column. Now, this is similar to crude oil, where the top of the fractionating column is where the lowest boiling point is. So it is important to note the lowest boiling point is found at the top of the fractionating column. On the other hand, oxygen with a higher boiling point of minus 183 will be collected nearer the bottom. Now take note, these are negative numbers. These boiling points are negative numbers, so you will need to be able to compare them carefully. Minus 196 is lower than minus 183. Okay, and finally, for the last part of this video, how can the volume percentages of the gases in air be tested? Now, very commonly in the TYS as well as in practice papers, you will see such experiments where you heat copper or iron with air in a syringe. So, the idea is copper, air, there is a reaction. So, what does copper react with? Copper metal reacts with oxygen. So copper metal reacts with oxygen in the air to form copper 2 oxide. Okay, so you are told you have heated copper with air and you use 200 cm cube of air at the start. So 200 cm cube of air was passed over heated copper until the reaction was complete. What is the final volume of air remaining? So this is a very important concept. What is this final volume? Final volume is the volume that did not react with copper, meaning it is actually air minus away the oxygen. Okay, so it's important for us to take note. The final volume is actually the air, 200 cm cube in this case, minus away the volume of oxygen. So now, if you look at the solution, it is presented in this four-step thinking method. The first step is to realize that copper reacts with oxygen. The second step is to work out air contains 21% oxygen. 21% of air, 21% of 200 cm cube is 42 cm cube. So what we are trying to say is in 200 cm cube of air, I only have 42 cm cube of oxygen. So only 42 cm cube can react with copper. Hence, the final volume of air remaining left behind is 200 minus away 42. The air minus away the oxygen. 200 minus 42 is 158 cm cube. All right, so the final volume of air remaining is 158 cm cube. Now I've appended one more question at the bottom for you to try out. Okay, the answer is also there. I would like for you to apply the same 4-step method to think through how to do the think question at the bottom of page 2 and see whether you are able to get the same answer as me. If you do have any questions, please approach your subject teacher to ask when we come back from the HBL. Okay, now this is the first of the 3 lecture videos, so please do continue to watch the other 2 lecture videos until we have finished the contents for this chapter. Okay, thank you very much.